I did want to talk specifically about the future of designing devices, development, commercialization, looking at big data sets, using artificial intelligence, machine learning, and deep learning approaches, but more from the perspective of a cautionary tale. So in summary, the points that I'll cover are how to pioneer the future, what precision in medical devices means in approach and in content, and then AI, ML, and DL. So again, artificial intelligence, machine learning, and deep learning, and quantum computing. Applications and caveats. So how these have been applied, how they can be applied. I'm sure a lot of you in your organizations are already using some forms of AI. And then some of the caveats I wanted to mention are empirical tales that we have from companies that I've worked with and many others in the market that have tried and failed or tried and succeeded wildly. And then I'll finish up with the neuroscience of innovation and where the markets all stand as far as all this is concerned. So it's easy to create unnecessary complexity, I think, is first and foremost an important theme. We can all build trappings so that our approaches to what we're doing with design and development and deployment of new technologies can become more elaborate than they need to be. And so like in the case of this particular cartoon, we can create situations where we're going from something that was maybe work from home monitors to an EVA layer. I would suggest here that precision is not synonymous with accuracy. It may be more valuable for all of us in healthcare in general to be more accurate sometimes at the expense of being less precise. And so I'll talk about that in a little bit of detail here. So accuracy versus precision. It's important that for you, for your devices and for your business approaches, to look at a series of operational and philosophical decisions from the perspective of, do we want to have greater accuracy in what we're doing, or do we want to go for more and more precision and the difference therein? And oftentimes, as I'll suggest to you and argue, that it's a balance of both. But if you hadn't considered it before, there basically are the differences. So statistically, there are ways to model the error variances and differences in accuracy and precision, but you've got on the left target there something that's accurate, meaning everything is biased around, just about around the bullseye. You have something in the middle which is more precise, meaning the systematic bias there is less, so you have points grouped together, but they're off-center. And then you've got in the third one something that is accurate and precise. And ideally, we would all like to be there for everything that we're doing. But sometimes we're striving for precision when what we need is greater accuracy. And sometimes instead, we're striving for accuracy when what we actually need is to tighten up our shots on goal and the approaches that we take. So here's how it can look for us as well. If you take a look at the top left target, you can be precise and accurate again. If you look to the right of that, though, if you're precise and inaccurate, that can point to systematic errors. And so how would you migrate your data cloud upwards and to the right? You can also have situations on the bottom left where you're imprecise. So you have reproducibility errors. So that is something that's oftentimes organizations have a difficult time divining from their data. And then again, if you couple reproducibility errors on the bottom left circle with the bottom right circle with the systematic errors, you have something that's not only imprecise but inaccurate. And in your various processes and businesses and corporate strategies, these can manifest in a lot of different ways. But if you've got a precise and not accurate approach, what you can have, if you look at the first time series plot, the trend line, is something that's relatively stable because you have precision, but it's off target. So if you were trying to shoot for that center line, the dashed line, you've got some tightly coupled data points there without much variation, but they're not where they need to be. The next one, you might have a trumpeting of data. So you've got no accuracy and no precision. And over time, your time series plot can look a lot more spiky like this with aggregate noise and growing uncertainty over time. You can have, in the third example, accuracy but not precision, where you have some sort of cyclical effect, and it would be great to increase the stability in your outputs and create more precision there. And then ultimately where we would all like to be ideally is to have stable and accurate processes where not only do we have a situation where we've crushed down the error variance in all of our systematic data points, but they're also hovering around where we intend them to be. I think a lot of what this boils down to is understanding that what you think you know may not be objective reality with our technologies, with how we use big data, with how we apply innovative approaches with AI, ML, and DL, and various other technological innovations, frankly, in devices. And my subtitle for this one is, "Or your brain can be your worst enemy." I had a hard time getting the motion on this slide to convey when I sent it to the background. And actually, it's just a joke. This is not moving at all, as a matter of fact. This is a still picture, but as is always the case with optical illusions or these so-called brain failures, this makes you think that the cylinder is continuously rotating, even though you may not want it to. So this comes at us in the form of, for example, looking at big data sets and thinking that we see things that are there, not really understanding what the technology could or should bring us versus where we're at now and where we actually intend to go. So it's easy to make these what we call commission of errors, these psychological fallacies that we internalize and then contribute to what we're doing in businesses. Here's another example here. I would ask the question, which square is darker, A or B? And by asking the question, you, of course, know that this is a trick question. If you suspend your disbelief here, it's actually true that both A and B are the same shade. And I did actually a color fill of the two squares. So I used Windows in order to color dropper. So whether or not you believe it, your brain is actually fooling you here, because the B square is the same color gray as the A square. And what's happening is your brain is trying to subtract out the shadow from the cylinder and therefore make you think that the B square is actually a lighter shade, but it isn't. So again, your brain at work doing what it does best. And this one, tends to really boggle the mind. This again is a still snapshot. So taken from an original JPEG and reprocessed as a static JFIF image. There's nothing in here that's actually moving. The only thing that's moving are the optical saccades in your eye. So again, telling you things that aren't really there. And sometimes we read into technology and big data sets and AI, things that aren't there, shouldn't be there. And that's really the caveat here, the cautionary tale. So if you remember Skynet was the neural net-based artificial intelligence system in the Terminator movies, created by the fictitious Cyberdyne Systems Corporation. And, interesting enough, on 12 June 2007, this was a day that in reality, so not in Terminator land anymore, that a robot called Adam ended humanity's monopoly on the discovery of scientific knowledge. So a computerized robot with AI, which was dubbed Adam, identified the function of a yeast gene on its own. And it elaborated about 19 hypotheses about this and was over 90% accurate in these test hypotheses. So they fed it some information, they allowed it to search public databases. And so in looking at Saccharomyces genetic functioning and different enzymatic reactions, Adam was able to elaborate on thinking that people hadn't yet done. So very interesting, I think, and it sort of points the direction to what is the future going to look like in medical devices as we incorporate more of these machine and deep learning innovations and other technologies like quantum computing. The future of AI and machine learning, I would also suggest, really started coming into its own in Garry Kasparov's match with Deep Blue, if you remember this. I ended up back in 1996 and 97 listening to this on a radio broadcast, so it seems really old-fashioned, but I guess it wasn't that long ago. They had a 6-game match in 1997. So the year before in Philadelphia, Gary Kasparov beat IBM's Deep Blue computer. And then what happened was 1 year later in 1997, they had a rematch. It was Gary Kasparov again versus Deep Blue in New York City. And in this match, unfortunately, Gary Kasparov fell to Deep Blue 3.5 to 2.5. So this is a picture of what the game actually looked like in practice. So you've got the proxy for IBM's Deep Blue on the right side, close to the image, and Gary Kasparov in the brown suit. And this image is what the overtaking of humanity by artificial intelligence looks like. So this is clearly an indication of where we'll all find ourselves, and we should be able to harness these technologies for our advantage and not let it be a subtractive anti-asset for us. I would also ask you to remember, if you do so, thinking about Google's latest AI/ML algorithm, which outperformed radiologists in detecting lung tumors. So this happened just about a year ago, a little over a year ago. And so Google put together this machine learning algorithm, which improved the accuracy of lung cancer diagnoses. And so you can see this article in Stat was from May 2019. So in that, I pulled out some of the data from that research, and what they did was they looked at 45,000 chest CT exams, and the results were compared with the performance of 6 practicing radiologists. And the algorithm achieved an area under the ROC curve of 94.4 and performed as well as the 6 radiologists. But the team, interestingly, reported a reduction in false positives of 11% and a reduction of false negatives of 5% compared to the true radiologists. When prior CT imaging results were not available, the algorithm outperformed the radiologists. So again, we're more than a year into a situation where in looking at even complex digital visual information, machine learning is capable of outperforming humans who are doing this sort of work. But again, there are always caveats. Sometimes the data visualization reveals hidden structure in the data, and sometimes it tells you to stop looking. So these were some real curves trying to fit whether control or active substances in the pharmaceutical world had any difference. And, again, trying to divine the truth and reality out of something so noisy. You can come up with best fit models, but oftentimes, as the eminent statistician George E.P. Bach said, all models are wrong and some models are useful. So some innovative applications that have been achieved with AI, ML, and DL. And to prime you first, I put together this subset graphic here. So artificial intelligence, the broadest circle, boundarizes each of these others. So within artificial intelligence, which is any of these techniques that mimic human intelligence, you have machine learning, which is a subset within that, and then a subset within machine learning is deep learning. So machine learning refers to a smaller subset of AI that includes abstruse techniques that are typically statistically based to enable machines to improve at tasks. And within that, we've got deep learning, and this subset includes algorithms that permit software to train itself. And so it can do things like speech, like image recognition, by having multi-layered neural networks looking at vast amounts of data, and importantly, being able to back propagate. So when it thinks it's achieved success or it runs into an error, it can back propagate to different steps in the process whereby it needs to replace previous information with what it thinks that it's learned. So some healthcare innovations that are currently using these methods include, as I said, the radiology example, so outperforming humans on lung CT scans from a year ago. And then interestingly, if you look into some of the healthcare systems data therein, the demand is something that's important as well. So not only just the image accuracy and precision, but the overall demand for reading radiograms is about 1 image every 3 to 4 seconds. So if you think about that, if, let's say, elective procedures increases again after the COVID pandemic begins to lift, and we've got this customer tact requirement of 1 image every 3 to 4 seconds, if that gets sooner, 1 image every 2 seconds or 1 second, we essentially are going to be burdening those who are reading radiological outputs. And so to be able to add to the situation, AI and ML can only be an asset. Microsoft had Project InnerEye, which was segmenting and identifying tumors, and they used machine learning and 3D radiograms for this purpose as well. And patient records in healthcare systems, of course, like I mentioned with the demand in radiology, patient records are now exabytes in size. So we're talking like 10 to the 15 in terms of total scale. And the caveat again here is we're looking for hidden patterns. Or the flip side of that is, are we creating fictitious patterns because of big data? Guided surgeries also have been benefiting extraordinarily from some of these approaches. And then testing drug candidates much more efficiently than we ever have. So being able to look at, again, large data sets and rule in or out candidates much earlier than we've ever been able to has been an asset, especially right now in the COVID-19 landscape with a variety of treatments that were part of the Solidarity World Trial. Also, on the healthcare patient centricity and services side, pattern matching to improve healthcare operations management and patient experience. So those surveys that people often get and don't like to fill out, surveys aside, there's a lot of work that's being done and has continued to occur to improve healthcare operations management. And this is important from those activities which are patient facing and how to improve the efficiencies and effectiveness within the treatment systems themselves. And so machine learning has been helping a lot in that, and frankly, saving tens of millions of dollars overall, which is expected to expand rapidly. And for example, to that end, so not only have I seen in healthcare systems tens of millions of dollars worth of savings, which in the grand scheme of things is very small, if you look at the broader scale and greater adoption trajectories, the hockey stick will occur. So McKinsey sees AI delivering global economic activity of around $13 trillion in the next 10 years. And in the short term, research firm Gartner expects the global AI-based economy to be about 3.9 trillion by 2022. So not much time for that to climb by a lot the next couple of years. So I wanted to mention one of the important concepts, which is patternicity. So seeing things that may or may not be there. This is Building X, a 19-floor office building in South Korea, which in 2020 was the source and site of a COVID-19 outbreak. And all those who are positively identified as cases are shown in blue. And those individual cases were put into some different modeling software to try to figure out how spread occurred. But now you have to remember that some of the PCR and antibody tests are upwards of 40% incorrect. And then, of course, you've got modeling errors from the computer ML itself. And so you could be finding things and potential vector transmissions that aren't necessarily there or aren't real. So this is something that Michael Shermer has called patternicity. So finding things that you think are there because our brains have been calibrated to that. So I like to call it fiction in plain sight. And so here's a few images for you of things that make us think that there are things there or not there. And the thinking is that this is an evolutionary adaptation where if you imagine something to be there because of a pattern, in the past it would have saved our ancestors from harm, because it's better in this case to commit a false positive and think that there's something there rather than miss it, call it a false negative and be attacked by something. So there's the predator there. And here's another predator. This is an owl looking away on the left side image and then looking towards us in the right side image. And I did find the original photographer's output of this because I originally had thought this was photoshopped, and it is not. Pretty amazing. Now, for your programs and campaigns, nothing beats good data, or does it? And this one didn't seem to paste properly, but the point is you can still read this one, so I'll let you go to it. So yeah, the gut feelings, believing what comes out of a model just because it's a model is always a dangerous game to play. And then in summary here, I wanted to just end with, as promised, thinking about the neuroscience of new innovations. So I had done a lot of work a long time ago in the field of neuroscience, doing different measurements of norepinephrine activity, dopaminergic activity under different conditions. Now, none of this work that I'm about to show you is mine, but I still think that it holds an important place for our industry as well. So we're all motivated oftentimes to innovate and to bring new ideas and concepts to market, but being motivated to innovate is not the same thing as innovation itself. And so this paper comes from Frontiers in Behavioral Neuroscience, and it's from Anselm and Robinson. And they looked at gambling, interestingly enough, and mesolimbic dopamine release and incentives. And I want to connect this kind of, like I said, in finale to the market. So we're always trying to add the newest things, the newest innovations, put in the newest technology. And similarly, the market is incentivized to want us to mention and use AI more, and machine learning and deep learning and 3D printing and quantum computing. And we should be, but remember, not only be incentivized, as this paper might even suggest, with the dopaminergic release of innovation, but the market as well, because something that's new is intrinsically motivating and interesting. So it could be any of the new technologies that we're trying to release, but sometimes we're just not there yet. And for example, with GDPR in the EU, Articles 13, 14, and 15 remind us that algorithmic opacity is a big problem. So if we don't know what a big data set is doing, if we don't know how a machine learning or deep learning algorithm has come up with a result within the healthcare world, we right now with GDPR are hamstrung in being able to use it, because Articles 13, 14, and 15 say that you need to have transparency in your algorithm. And if these are coming up with algorithms on their own, and I know of several cosmological models which have fallen into this trap, if we don't know how the machines came up with the answer, we can't use the answer to elaborate treatments for the public use. So this is a kind of a zoom in of a snapshot here from this paper. And interestingly, it says that several payoff schedules, like those in some slot machines, roulette, and the dice game craps, have a probability of winning close to 50%. So the house almost has no advantage. And they would be expected to elicit maximal dopamine release and therefore reinforce the act of gambling. But the evidence that uncertainty itself appears to be a source of motivation is visible in the growing trend of pathological gambling, and it talks about video poker slot machines. And they go on to say individuals are playing to play rather than to win. And the monetary wins are conceived as the opportunity to extend the duration of play rather than the game's main objective. And if we think about this in the context of our industry, we sometimes are motivated by the very fact that we can innovate itself, and not just that innovation is bringing us closer to a final goal. So I would say, coupled with the other caveats in the cautionary tale, it's make sure that we're doing things for the right reason. It's the game itself that's making us want to play. So it's all of us who have to help guide investors in the market as to what the best innovations are. And if it's not what let's say, the shareholders think that they are, then we help course correct them. And with that, I'll stop sharing. Thank you very much.